Hi, I'm Shin from 4781, the Mechanite. So over the season, many teams had problems with TensorFlow object detection that are building into the FTC SDK, from not getting an accurate skystone result, having the wrong skystone detected, or just not having skystone detected at all. So teams are trying to use third-party library like OpenCV, the FTC lib, and just use color sensor to do skystone. The problem with third-party library is they are very accurate, but it's unavailable to onboard Java user or to block users. So in this video, I'll try to educate people how to use machine learning in their program and how to properly train them, train a machine learning model in general to use in their program. So the problem with this year's TensorFlow model is that first didn't train very well. It's only trained over, I think, 30,000 times around, if I remember that correctly. And their dataset is not very good at all. So what is TensorFlow anyways? So TensorFlow is a machine learning framework that's created by Google and is the most, according to GitHub Star repository, it's the most popular framework out on the market. And it's used by a lot of companies too, like Intel, Airbnb, all the great companies are all using TensorFlow. So I'll say TensorFlow is a very good framework. It's a very powerful, very cool framework. It's just a model that messed up the entire reputation of TensorFlow in the FTC community. And this tutorial is not only to FTC, but also FRC and potential any other application you might need, because all the training process will exactly be the same. So let's get started. Alright, so first thing you'll need is TensorFlow, of course. So you can get TensorFlow from the tensorflow.org, the website. And for the sake of simplicity and for the ease of use in the future, I'll suggest use Anaconda. So what Anaconda does is create a little virtual machine. Well, it's not totally a virtual machine, a virtual environment to your specific need. So for example, if I have a web development and I have a deep learning development, I want the web development only have the web package like Django or Flask, and for the machine learning environment, just have TensorFlow. So I would suggest use TensorFlow. Just if you are just still if you're just doing TensorFlow, I would suggest to get Anaconda. So from here, from TensorFlow.org/install, you can find all the details onto how to install TensorFlow. And for this specific reason, by the time of recording this video, is 2020, and the Skystone season is over. Well, this year's game, 2019 to 2020 game is Skystone. And why it's over is because there's something called a coronavirus, COVID-19. If you're watching this in the future and wonder why there's a year with no championship, that's why. We cancel everything because of the COVID-19. So that's about that. So you want to navigate down to pip and install the older version of TensorFlow, because the thing I'm gonna use is called a TensorFlow. Where is it? TensorFlow Object Detection API from the official TensorFlow GitHub. It's not currently supported by TensorFlow 2.0. It's the latest version of TensorFlow. If you're watching this in the future, or it will be supported, just check back at the TensorFlow Object Detection API repository. By the way, it's still this URL. I will post all the URLs I used in the video description and on the GitHub as well. So once you got TensorFlow, once you got Anaconda installed first, and TensorFlow installed inside Anaconda, then you want to clone my repositories, which is FTC-TFOD. So for this repository, I didn't wrote all my code by myself. I would still like to thank the original author. All the original author actually is from Google/FTC Object Detection. They done an amazing job of getting everything started. But as you can see, it's about 2 years old, and due to the fact TensorFlow is evolving really fast, some of the package was deprecated and some of the code just doesn't work anymore. So that's the reason why Homemade Ripple just poured everything back here. And if you are interested, the TF object detector is what they use in the FTC SDK, the library that they used. If you want to modify that, you can do this mode, and I don't think. Yeah, you can do. You can plug this back into the robot controller if you know how to do that. I will not do this time because it just is fine, because and it didn't change a lot. So it must be stable. So I will just like to thank all the teams that who did the original one, and I still love them. But due to the number of additions, subtractions, like all kind of modifications, it's not really good idea to merge back to the original repo. So that's one right here. And the second thing I want to talk about is the TensorFlow Object Detection API. So you want to install this first. Install this after you finish install TensorFlow. So you can follow the step installation process under here. It's all laid out. For Windows, there's a few things you have to worry about Windows. One is the portal buff, and one is the COCO API. So this thing have a little problem running on Windows. So you can just go search this out, and I might make a separate documentation on that because I don't want to use this too much of video time. So after you get everything installed, so basically Anaconda, TensorFlow, the object detection API from TensorFlow, and the clone, download the FTC-TFOD repository. You want to open your IDE editor. For this time, I'll use PyCharm because that's my mostly used IDE, and that's where the IDE I coded all my project on. So we close out that. So let me explain the file directory of this. I will not go alphabetically. I'll just go by the importance of the file. So first thing I'm gonna say is called a labeler. The labeler is in machine learning. It's just something called a labeling process. It's basically take an item, because for this is a pen. I want to label this individual as a pen, and this is a very tedious process in machine learning, except the training process, which also time consuming. Just sometimes in the industry, in the professional industry, there's always someone will label the image for you, but this time we just need to label ourselves manually. So this is a little script that basically display an image, and you can drag along the line to place where we'll show all this script running later in the video. And so next we're gonna talk about the FindBB. So FindBB is a script that lets you find the initial bounding box. So labeler.py is fully manual, so you have to drag the line every time it's a new frame. So now we're moving a little bit to the semi-autonomous method. So first script you want to run is called FindBB. It's finding boxes. So you know that little box it put on the reverse. So like this. This is the model I trained during the Skystone season. Unfortunately, it has been ended. Just the last time I created is months ago. But this is what a bounding box looks like. So see all this red box is called a bounding box. It basically basically have a box around the thing that's being detected. So after that, you have something called a tracking.py. This script is a semi-autonomous method to label an image. So this what it does is have some OpenCV image tracking algorithm to semi-autonomously label your image. So this is not very accurate. You still need to sometimes manually correct it. So that's why I call it a semi-autonomous, not a fully autonomous method. If I have that, we did not train neural network any soon. So all the manual you can find in documentation, but if you need some reason from here's just description on how to using this as well. So next is some utility functions, the BB box writer, the join utility, and this is to write the bounding box as a label. So the label is where it's x, y coordinates being recorded, and the label is being placed, and the join util is the screen you will see later on in the video that basically create the screen of the labeling software. So one more is called convert labels to record. So this script is a TensorFlow utility script that will convert the txt and the image file into a file that TensorFlow will recognize and train on. So we don't have to worry about that really for now. And let me now explain the folders, the few folders here. So the model folder contains the network that's pre-trained using the COCO dataset. So you might wonder, hey, what's that mean? Is the model already trained? Where I'm getting it from? So we're getting a model called. So what we're doing now is called a transfer learning, where we take already trained model and feed our data into it. So we got a new model of it. So what we do is under the model tool. So that's where all the pre-trained model in the COCO dataset. If you don't know what's COCO dataset, search up is basically all sort of data element trained together on a really a powerful computer for like a week or months, like even more. So basically it done some of the job for getting the network familiar with image first. So for this time we were using SSD, stand for single shot detection, which is one image given to it populates all the bounding boxes and it detects. It's not similar as YOLO. YOLO is like just another different type of algorithm which the image there and it drops all kind of bounding boxes and it just detects. That's much faster, but unfortunately it's unsupported by TFOD for now because it's other kind of machine learning is called darkening. So we're not talk about that. So we're not focused on it's called SSD. MobileNet is the network we're using, the deep learning network version 2 and quantized COCO. So you want to ask, hey, what's quantized? So quantized is basically you from a really high resolution to a lower resolution. So what this does is give it a more faster output. So compared to a 32-bit floating point, it convert back to a bit number, which is you lose some accuracy, but you'll get more speed out of it. So, and another reason why is because at this time the FTC SDK version 5.4 is locked down to use only quantized model. I opened this issue on FTC SDK, so please don't go and open again. They closed it. I think they are fixing it on version 5.5 next season. So I hope you can use more model like MobileNet V2, the full-blown 32-bit floating point model. So I'll just stick with that. So you can download this right now and should be done in a moment. So first what I'm gonna do is to import a model. So once you download it, you want extract it, and once you export it, should be have something like this. It's called a SSD underscore MobileNet with quantized 300 by 300. So what this number means is basically it's given a 300 times 300 set info. So no matter how big or how small the image is, it will always get down to a 300 by 300 resolution. And it's trained on COCO dataset. The last time the time it's been exported is on 2019 January 3rd. It's about more than a year old. So but still okay. We'll train our data on anyways. We don't need their own models. So what we're gonna do is to models. Just gonna copy this into the models folder. I'll say okay, and let's just give this simplicity. Let's just rename this and erase everything after it. So we know it's a SSD model version 2 quantized model. So next thing I'm gonna do is get some training data. You can get training data from what I already collect from the Google Drive. Basically I have two folders, a training data, which have all the videos that's having a stone or a sky stone. So if you want to use your own data set, here's something you want to wear off. So be sure to have good lighting, preferably the lighting that will match at the competition. Several pictures taken from several angles, some extreme angle actually, because your robot gonna move back and forth, looking back and forth, maybe just undershot or overshot the stone. So you still want your network to pick up. And third is have a composition of stones in your videos. For example, like this. I have a lot of stones in here. So you can see I'm taking the stone from a lot of angles. As for the validation dataset, you'll always want to have a very near world validation data. So you can see I took this basically at the same time. I just made the network feel more challenging. So after you have all this data, you have your training data, have a video, you have your validation data, and now we can start labeling. Okay, now let's start labeling some images. So for now, I'm just gonna start with fully manual labeling, like using the liberator.py script. So I'll type Python labeler. If you don't know how to use it at first, just press help. So I will need a few arguments. It's actually very simple. So you will need a file name, definitely a file name. So here are some key you will need during the training. So the spacebar is to pause, Q is to quit labeler while it's playing. So that's some very helpful keyboard cut, and H is to step backward, and L to step downward if you want to do manual training, not autoplay. And here's something you gotta remember while you are doing your training. So backtick, so the key next to 1 is called a backtick. So while you're pressing the backtick, you can press A to Z, any single letter, to make your label. But for this time, I only have 2 stones. Mostly, it's just in FTC images only 2. FRC might be just only 1. Only for this year, for example, the infinite recharge only have 1 power cell, which you just need to detect power cell. Just one that one element. So you don't need anything more else than fancy. So you can use the mouse. So the mouse will draw the bounding box, and C is to clear all bounding box on the current frame. X is to undo the most current, and R is to load the bounding box from the previous frame. Okay, so that's basically how you use it. So let's just use our train data. If you see I'm clicking, it's called a tab. Tab is for autocomplete in command line. So I'll just training data 1. Alright, so here is the labeling utility. So as we described earlier, so we're gonna press backtick, so I'll choose my current class as S for Skystone. So as you can see here is current class is S, so I was just labeling Skystone like this. And for regular cell, I just name it R for regular. And basically, for now, I can label also, or maybe just label this as well. Label this and label this. Okay, so as the manager described, we press N to go on the next frame. So for each frame, as the default is to skip 10 frames to the so from 1 to 10 to 20, like that. So for now, we can just start labeling our second frame. So backtick S, Skystone, and stone, and let's have some regular stone. So you guys get the gist of it. So you're just gonna press N plus backtick plus the label, and basically until the frame stop, or just press Q to quit. As you can see from here, we already have labels. So that's the coordinate, and that's the label class. And you can see that's our image screenshot getting from the labeling software. Alright, now let's do some semi-autonomous labeling. So first script I'm gonna run is called BB. It's called finding box. If you do not know how to do it, help is very helpful. Alright, so we'll do train data. We'll do this on training video 2. Alright, so here's the window. So for this one, I only have 1 block, which is easier for the tracker to do. So I'll just go backtick, and for that actually, you don't have to backtick. You just need to press E to Z. So I just need to S. So it's a current class S. Bounding box over it, and I'll just press Q to quit. I find the initial bounding boxes. So next, we'll use the tracking program. So as you can see, tracking, we can have some options. So for example, the first one is always the file name, train data. So we'll use train data video 2, and for the tracker, as you can see here, I always use ML. So you can count 0, 1, 2, 3, 4. So the index of 4 tracker. And for frames, the typical frame, I just leave a 10 for just default. If you want to have more frame because you have very less data, or you record a very short video, I would suggest you change the frame to something small like 4 or 3. And that's it. I'll just press 4. Okay. So first of all, it will bring up a window to confirm is that the bounding box, initial bounding box that the tracker was locked on. So I'll just basically answer, press Y to yes. Alright. Alright, so this will bring up a few windows. Okay, so by the way, it's the pause is still space bar. So I'll bring up a couple windows here. One is the tracking window, which you have a adjust to the bounding box around it. And the second one is the frame that has been saved onto the disk. And this little window under here is what the bounding box is looking at. So this will be scaled down a little bit, so just follow the yellow line around it. So that's where your actual bounding box is being reported back to the TensorFlow later. So press go. And the frame rate will depend on your computer. I have a Ryzen 7, so it's not bad. And for this, it's all using CPUs. So just let it track. Getting more data set. So this is the image, as we said. So you want to keep the bounding box right on the stone. So that's why I call it semi-autonomous. You have to really lock that thing on, otherwise it will just not work very well. Okay, so after you label some, I just having a little experiment. So you will have a label that's been created for you already. So that's all the auto semi-autonomous generated labels on here. You can see this and the text, the coordinate. But also that you can also get a screenshot of where each label is being overlaid on top of the source image. It's from the rect under the frame of the picture. But you can do, if you want to do something more interesting, you can view the video that has been generated while it's labeling the picture like this. Alright, so you can see we're trying to fix the bounding box here. The bounding box keep sliding. Alright, so you get how both the tools work. One is for semi-autonomous, one is for totally manual labeling. Just remember, when you manual labeling the image, just remember to have just every frame you dump, you make sure to have some label on there. Otherwise, it will just mark as a negative image, which means doesn't have to tell the deep learning network to have nothing in there. Alright, so after finish the labeling image, whether it's semi-autonomous or just manually labeling, you will get field folders. Basically your image, and your label file. That's the most two important thing you'll need. Second thing, we're gonna check for if there's any bias in the dataset. So for bias, which I mean is how much item is in each label. For example, you have too much stone, the network might be just biased to just stone. If you have too much sky stone, the network just might be biased to like just sky stone. So we'll just keep the network balanced for now. So very easy thing to do is just check how much item is in one of the folders. So what you want to do is just basically, if you are using semi-autonomous tracker, just divide by the number by 3, because you have one image file, one txt file, and one composite file, which is a screenshot of the saved frame. So this one has 100 image of a stone. Let's check another one. This have basically not 100, but this won't really matter as long as keeping your like 20 to 30 range, not like 100 stone and like 20 sky stone. Just within the range that the network will pick up. The third one is basically have a stone and sky stone in the same image. This will be the best case scenario when you're trying to train network. Just have balanced. We have each class in their one image. So this one have around this one have a lot. This one have around 300 images. So I'll say this is a okay network. Slightly biased to stone, but for the sake of tutorial, just quick and easy. So the next thing I'm gonna do is run the convert label to record. So it's basically convert the label we just created, convert the image, convert to something that TensorFlow will understand. You might notice here I don't have validation data, and you don't have to have that as well. But I said it's good to have that. If don't have that, So we're gonna randomly shuffle from the dataset here. The random shuffle I just having like couple frames inside the validation data to feed back to the model. So okay, let's generate some record. So we'll use the convert label to record. All right. So and there's one more thing. If you're using NVIDIA GPU on Windows or on Linux, you can use the TensorFlow GPU library when you are installing. So if you're using AMD GPU, I haven't tried that yet, even though I have an RX 480. I heard it's pretty fast, but for the simplicity, and most of the people are still running on Windows, just try to install having an NVIDIA graphics card. It just need to be compatible with 3.5 and higher to be compatible with TensorFlow. So for now, I have a GTX 1080 in my system, 8 gigs video memory. So when you're trying to just pick a graphics card for just training purposes, I just you pick a high memory graphics card that will just fit more stuff into the video RAM. So I don't know about that. So thing what I need is the folder, which is it's called the train data, and we have this flag is set when you don't have a validation data. That's called a -e. So what it does is randomly shuffle, like what I said, randomly shuffle from the training data set to have some pictures, some image picking out, and just be the validation data set. So I'll just do that. And if I want to do a custom weight of the split between the training image and the validation image if you are extracting from one single image, it's around 0.25, but you can be any point you want, just not half, because you want most to be your training image, otherwise you have no training image to work with. Just have like 30% of your image in your training data set for evaluation if you don't have the validation data. So I'll just press enter, and now we're gonna split how many files we're gonna split. So basically we don't want to stick everything to one giant file. It's very hard to move around if you're doing like distributed computing environment to set up to somewhere to the cloud or send back to your school lab. So that's very easy to split around your training file. So for this time I'll split around 8 files. And the split between the training data and the evaluation data, I'll just do 25. And this will take a while, depend on your CPUs. Using Mac thread, as you can see from my task manager, if I can open that. Yep. It's using our course. It's doing some very heavy intensive. Okay, it's done. The runtime will increase depending on your TPU and amount of data set you will have. And you can see here we have some we have 2 labels. So I have Skystone, the 0 label, the exact 0, and Stone 1. So as you can from here, we have a pretty balanced. The summary is we have a totally really balanced. We have a 300 Stone image and we have 290 Skystone image. So we have 0 negatives. So what negative does is giving the TensorFlow, the network, a file that's basically nothing. If it's detected, it does need to be retrained. So negative is not to have, but it's not required. Alright, so as you can see from here, we have all kind of record file. We have eval, which is evaluation, and the train as where the train will happen. So next we're gonna prepare our model. Alright, so now we're gonna prepare our model files. So as from the beginning, you will download the SSD mobile network to content file, and from here we'll need to do some modification to the pipeline config file. It's basically how your model is being defined under the retrain. So first thing you're gonna need is change is to network classes. So we'll have 2, Stone and Skystone. Oh, by the way, if you're using Watch the Future, and the FTC SDK released a update where you have option to change a quantized model or non-quantized model, I would suggest you use the floating point model is more accurate. For now, I just quantize. The config shouldn't be really much different. It shouldn't be really different. Alright. So first thing is modify is the number of classes. We only have 2. Well, I can go down here to this, the fine tune checkpoint. So this path needs to be a absolute path on your work system. So here, you can see I have my models quantized. So I'll just copy this path to be configured here actually. On Windows, maybe you're used to backslash, but / works just fine, or just automatically come back to backslash in under the hood. The next thing I need is where's the training data is located. So we're back to our training data. So let's just copy this training data. Path to be configured. Just paste here. Let's do a quick replace. I will replace that, and let's copy the training data. As you can see from here, we need edit our label. So our label is label.p label, and our data set will be here. And let's do a quick replace. Alright, train data, and we'll have our train record, train-record, and we'll have the record at the end. And you may be asking, oh, we have this -07-00. How can we tell the TensorFlow training to look for that increment? So here we're gonna use a train dash question mark. So this will scan from 00 all the way to 99 till it's didn't find anything. So this defines how many place of digit it will have from 00 to whatever the highest will be. And this will next we're gonna focus on the eval input reader. So this is the train input reader, which is reading the training evaluation data, and this eval is basically reading the evaluation data, the validation data. So we'll just copy the same label path. I like shuffle to true, even though we shuffled it. So just making sure we just didn't get unlucky, just get the same random number. And the input path will still have just change the train to eval. Alright, so basically that's about it. Yeah, and here's something you want to note about more: the evaluation configuration. So eval config. So number of examples is how much example gonna run evaluate every single batch. But we don't have over record to have over like 500 image total. So I just set this number of examples on evaluation to be like 20. And I do not need this. And up there is called under the train config is the batch size. So batch size is how much data are gonna fit into the video memory at once. So that's why I'm telling everyone to get a big memory, so it can fit more files in one run, in one single session. But for now, I have a really small video RAM, so I just put like 8, something really small. And that's basically about it. You don't have to touch about models, all tuned by like expert. And now we're gonna finish configuring the train configure our batch size, the number of steps, and this is also important. This the number of steps will is how many iterations TensorFlow will to train the model at. So this is really high number. So if you want to just start small and stop at a certain point, just put the number in and run, or just stop at a certain number point. So for example, if you want to train like 1,000 times, just put 1,000 here. After 1,000, I'll just stop. But now I'll just leave at this big number here. yes, then that's basically much about it, about the configure, well, about the model configuration. Next, we're gonna configure our training parameter. So under script is just under the script folder is some script I create that you can just run using a bat file. I know a lot of students and teams are running Windows, so I just create mostly on Windows, and I roll out this on Windows. But I'll add a Linux port later on for all the bash drivers there. Okay, so first of all, I'm gonna set the environment. So basically, what I'm expecting you to do is run from at the root. So basically, script run like this, not basically sitting into script and run all the script in there. I'm expecting to run all the script as project root. And so first of all, I'm gonna set the pipeline config. So I'm gonna models directory. We select the SAT model, SAT mobile level 2, and point to the pipeline configuration file. The next is called the model file. It's where your checkpoint or your version graph gonna locate at. So we wanna create this folder now. Save model. Okay. Let's create this model folder. And this basically is where all your session is, where your training session is stored. The third is the TFOD API. This is very important. So when you installing the TFOD API, I will tell you to export the Python file, and this is very important. Remember to do that as well. This will add into your path if you're on Windows, and I will give you a clear instruction on Linux as well. So basically, you want to do for TFOD API is navigate to your drive. For my case, it's D drive, TensorFlow files, and it's on models. So basically, I clone the entire repository. So models, research, object detection, and just basically copy the absolute path to here. And this is basically where your object detection API roots living. And that's basically much it for configuring the train file. So next, I will always like to run my training script separate with the IDE. So when I close the IDE, it doesn't stop the training. So if it's an anaconda, I was conda active FTC-TFOD. That's the environment I created. If you didn't install anaconda yet, I will tell you, the anaconda will tell you all the initial setup, how to activate an environment in their setup guide. It's basically better than me teaching it. And next, we're gonna see our project downloaded. So it's Python project and FTC TFOD. So touch CD. Yep. All right. So now I'm in my folder. So I'm now gonna run script /train.bat. And this will automatically set all the parameters and basically train your models. So from now, I just need to play the waiting game. Depending on your hardware, it may train from days to weeks to like even months. So the model. So at this time, I will just take a moment to talk about the model I trained. So for this model, I use same SSD mobile NAND way to quantize COCO dataset, and this is trained over a month. Let me see. Yes, actually trained over a month. More than a month now. So first release is on January 29th, and the last release is 18 days ago. So basically February 24th. This will go together like around 98% of accuracy when detecting sky zone. So I'm pretty confident if you have a good data set, you have patience for training it, you'll get really good result of the TensorFlow. I heard a lot of teams saying that TensorFlow is bad. It's not good for the game. I will admit that TensorFlow is really overkill. It's overkill for this game. So just look at OpenCV. Just basically, you are just measuring between the light of color brightness of the stone and the sky zone. Basically, stone is darker and stone is brighter. So and you can get a really like 100% accuracy, 100% every single shot on here, rather than doing like just deep learning style. But it's nice to have options, anyways. So I'll just let this sit, training it for like couple hours. then I'll come back with some result. Okay, so you have been running your model for like few hours, and you want to know how's your model doing. So now let's introduce a program called TensorBoard. So what TensorBoard does is give a nice graphic representation and some pictures, in this case for object detection, of what is currently under the hood, the evaluation process goes. So you want to open your command prompt and navigate to your model directory, specifically your checkpoint directory. So you're gonna just type TensorBoard dash logger and just press dot for the current directory. It will take a while to load. If it's the first time you open it, or just compile a little bit of the event file it will have. Once it's done, give a less URL, tell you, hey, it's that localhost 6 port 6006, and you can just go on here. You'll go on localhost 6006 and view your graph. You might look it's pretty empty, but as times go, your graph will look more and more just have loaded more and more graphs. The most interesting is about images. This is where the image that's been detected right now, and is evaluated for every single iteration that it goes through. So for example, you can see here we have our model is pretty accurate now. So because you have to read this really carefully. So on the left image has the detection detect, and the right ground truth is what's original. So you can see from here, that's 99% sky stone and 99% stones, and the original is like 100% on everything. So you will get a little bit just about how the model is doing like as it goes. You can scroll back. Unfortunately, mine doesn't scroll, but if you have more data, you can scroll back and see what data, how the model has been revolving, and try to learn and correct itself over time. But so this is a very cool feature about TensorFlow. Is one thing called TensorBoard. And after this, we're gonna export our graph and do some inference on actual video. Okay, so we just saw all this beautiful little image that the TensorBoard generated while it's evaluating the model. So how do we export this and run real video? So first of all, let me explain some thing that the training model is piping out. So the loss is the incorrect tensor. You want the loss to be as close to 0 as possible and not equals to 0. Because once it equals to 0, it means the model is overly fitted. That means something is wrong with your validation data. It could be the same. You feed exactly the same training data as validation data. Just copy cause loss equals to 0, just 0, not 0.0 something. And the step is how many tries did it take for the model to train. And for TensorFlow, every single step is 100, and you can see this from over per 100 steps is around 45 seconds on my end. So you can stop training at any time. Just press Control C. Yep. And I'll just terminate job and say why. Okay, so now we terminate our train. Now we can export our graph. So our model. So first of all, let's go back to our editor. So back to the script. First of all, export a full-blown just regular TensorFlow model. It's actually a technique called a frozen inference graph. Okay, so we're gonna go back to PowerShell. Let's go to script. We're gonna do export inference graph. But before we do that, let's configure some parameters to fit our needs. So first is your network directory. It's where your base model or network is sitting at. And the pipeline config is where your pipeline.config file live at. And the model directory is where your checkpoint, like model checkpoint with all this file located at. And the inference is where it's being uploaded. You don't have to create this folder or automatically create a folder. In fact, the folder need to be empty before it's being exported. Same as before, TFRecord API, and input image is because we are doing with image, it's the image tensor. So this you have to be really careful about the model prefix. So you see where we did is like a steps. So that's where we're gonna tell the model to look at the latest model check we generated. So right here we say our latest model check one is already sorted for us is 48633. So that's our model prefix. So after configure that, we just go back to our PowerShell and run the export. It'll take a few seconds to generate out. Okay, should be done just now. Okay, there we go. After it's generated, the frozen model file will locate it at the output inference class. And all there, what we really need is the frozen inference graph and the label. From now on, we can run some inference on our models. So we can now using this, the inference py and inference underscore TFLite. So the difference between the both files is one, the inference.py file is only meant for running a full-blown TensorFlow. So for example, here we're just running a regular TensorFlow, and inference TFLite, as the name suggests, is just a scale version down of TensorFlow. Like that's the version of TensorFlow that actually loaded on the FTC SDK. So this is really great tool to test your model, but it's not really good to visualize because TF-Lite is only optimized for the ARM processor, not x86 or AMD 64 instruction set processor. So just make a note of that when you just run TF-Lite. It might just be really slow. Alright, so let's run some tests. So let's run up. So Python, we're gonna run inference. If you still don't know, always get help. Okay, so we'll need a model directory. So model dir and script, actually not script, models, and output inference graph. This will point the script to where all your graph is stored. Like if your graph file is frozen inference graph.pb, you have to specify the next which is the graph, and you have to specify your label. If your label map is label.pb.txt, that you have to specify in the flags. And this you have to set the threshold. Mine is set on 0.5, is like half threshold, and the video is just the video file I'm gonna use. So we'll just overfit this model. It's a very bad example to do this. You are gonna run on a real validation video. So now we're gonna run our training video, which if I didn't remember is this. So after enter video in, just press enter. I'll do some little bit of math, do a little bit, plus push the graph into the memory, and here we go. We got our inference graph, inference data. So as you can see, the bounding box around the sky stone. And we can stop the inference at any time just pressing Q, and that will exit. So now let's export the TensorFlow Lite graph. So as before, I'm gonna run our export TF-Lite script. So for this, it's basically the same. Just need to have your model prefix match to the latest graph, and it's basically match almost everything here, but except your output directory will be at TF-Lite. So we're gonna script export TF-Lite. I'll do some computations or do some compression on the model optimization. Should be done relatively soon. Alright, now it's done, and we can now run the inference on TF-Lite model. So just like before, we have to select our model directory, which in this case will be TF-Lite. And our inference file will be TF-Lite. Oh, sorry. Alright, so I'll do a little bit of math, and there we go. So you'll be known as doing really weird thing, like just like the detections wrong, detections numbers not even correct, and so very slow. Just because, like I said, it's optimized for a ARM CPU. It's not meant for a like AMD CPU to run on desktop. The desktop is meant to be run on a full-blown TensorFlow, not like TensorFlow Lite. So just press Q to exit, and then you are done for inferencing. And all now your model is available at the TFLite is under TFLite directory, detect.tflite, and your normal TensorFlow file is under the output inference graph and frozen inference graph, the BB. And that's basically much it. You successfully trained, export, and inference your model that you made. Congratulations. Okay, so at this video, I hope you learned something new. If you don't know TensorFlow, now you know how to properly train a model, how to collect data, how to make labels, how to run inference on computer, and you can just export the TFLite model to on your FTC robot controller and just see the file right away. And I think at the end that TensorFlow is somewhat really overpowered for FTC competition, but it's a really nice tool to have, and you can also flex on judging. So I think it's a really good tool to learn, and it's because all the industry are using it, and you should just catch up as well. So I hope you like this, and if you have any questions, suggestions, comments, either video, the comment description, or just in the GitHub issue or GitHub pull request, if you want to make some changes to the code, that'd be really appreciated. So sorry for my poorly speaking skills. I hope you understand it. I hope you learn something new, and that's it. See you next time.